Hello. The system that we're going to look at now is the first of our sort of 6 systems. This is going to be the system to look at the rigid part recognition. These are going to be flat little parts sort of sitting on a desktop or something like that. We'll see some examples of them right here. What we would like to be able to do is take, a full big image, something like this, and be able to say, well, which part is it? Is it this one or is it this one? Notice there's a slight difference between the two. And we'd also like to say, where is it in the image? We want to be able to recognize the part and estimate its position. Once we've recognized the part, then we know which thing to do with it if you're building an assembly line or something like that. And if you know where it is, then your robot can go in and grab the part or insert a component or drill a hole or something like that. So we need to know both of those. The general family of algorithms that we're going to be looking at here is what's called model-based object recognition. We're going to use a geometric model like what we've looked at in the introduction to the lecture series, and we're going to build models of these parts using the simple modeling technique that we looked at, and we're going to use those models to be able to recognize the part. There are other ways to recognize the parts that are property-based or appearance-based, but here we're going to use geometric models as the basis for our recognition of the object. Well, this is what we want to do, our object recognition. In order to do that, really there's 4 stages, and that's these 4 bits right here, and we're going to go through those in sequence during the lecture. We want to start with a description of the objects that we see in the image. We're going to want to match that description that we've got from the image with the description that we've got from the model. Once we've got a good match, we want to be able to estimate the reference frame transformation. That's the pose of the object that maps the object, the model, into the scene or the image. And finally, because the algorithms that we use often generate false matches or false pose estimations, we want to be able to verify whether we've got a correct match and a correct pose estimate. And so we'll have a verification stage. Well, why do we want to do this? Well, a lot of computer vision in the factory area is all based around these sort of object recognition, simple object recognitions. You've got objects that come down on conveyor belts and maybe in different positions, different orientations. We want to be able to identify where the parts are on the conveyor belts. We want to be able to maybe do some inspection of the part to make sure whether the features have been properly formed. We want to be able to estimate positions, for example, on circuit boards if we're going to insert components into that circuit board or drill holes or do some soldering. This is probably the most common use of, let's say, sophisticated computer vision systems worldwide. There are more probably surveillance cameras around in the world than there are these manufacturing type systems, but most of those surveillance cameras have no computer analyzing any of the images. They just store the video, and occasionally they have some human beings watching some of those videos. We want to be able to do this at high speed as the parts come quickly down the conveyor belt. Why do we want to do this? Well as being able to automate the systems, we also want to do some kind of inspection. If you're producing a product, you want to have the best quality product that gets out to your customer. You don't want to have defects. You don't want to have things which might lead to injury or accidents. So therefore we have a lot of inspection of these kinds of objects in automation type systems. Well, we're not going to do anything sophisticated as that. We're going to look at a very simplified version of that. All of our systems are going to be a bit simplified. That's so we can get across all of the details of the system, so you can understand the concepts and how the pieces put together without all the sort of special wrinkles and special cases and things like that that you really need to do to make a real system. That's for Computer Vision 104 rather than 103. So here's the part that we're going to try and recognize, or an example of one of the parts we've got. We have our original image. We've done some sort of thresholding and binary image analysis like what you've done in your previous courses. And here is the image that we've got right here. Here's our geometric model that we've built using our modeling technique. Coordinates going around all the corners. And here we're going to be basing everything upon the edges of the object. So we're going to take this image, this binary image, and from that we're going to want to extract the binary edges that go around that object. And so you can see examples of some of those edges. Here's the vertices where the edges end, and you can see the straight lines that connect it up. It's not going to be perfect, so we've got a little bit of a kind of defect around the corner here where the segmentation hasn't worked properly, and so we get a little bit of extra stuff. Sometimes we miss some of the features as well too. So the image description is not going to be perfect, and that's one of the complications that we're going to have to deal with. But assume that it's worked reasonably well, as it has right here, and now we've got the problem of how do we match these image features with those model features that we described in the previous slide. So that's the first step, is doing that matching. And then once we've got the matches between a model feature and an image feature, or a whole set of them, we want to estimate the reference frame transformation that maps that model onto this image, or onto the scene. So that's the next step right there. So that's pretty much the whole matching type problem. We're looking at very simple matching type algorithms, but this is going to work very effectively, okay, if we have good properties. If we have good properties, we're going to be able to do good matching. While I've simplified this greatly, actually the algorithms we're going to look at work for a large number of parts. Okay, they maybe have some quite complicated shapes, but generally most parts need to fit in as part of an assembly of some sort. And the easiest way to build things that fit together is to have some straight edges and circular holes and circular arcs. That's how things fit together well. If you have a complicated curve, that's maybe where the air goes or the water goes or something. They don't fit together. It's more complicated to model that kind of stuff, but most real parts have a lot of straight lines, circular arcs, and circular holes. And once we have those, the techniques that we've looked at here are perfectly suitable for modeling and recognizing those parts. We could extend it to other kinds of features besides straight lines. I mentioned the circular arcs already, and I mentioned just about the holes. We can also add corners in as well, different kinds of features. But we really don't need to look at that here in the lecture series. Just looking at straight lines is enough to really introduce all the basic ideas. We can extend it to 3 dimensions. In fact, we're going to do that later on in the lecture series. We're going to look at how we can recognize 3-dimensional shapes, again using the same sort of technology right here. We can also extend it to perspective projection. That's where the camera is not in a fixed position, but maybe it moves around. And so the appearance of the object actually changes as the camera moves. Here we're just assuming that the camera is roughly in a fixed position, always looking at the objects from the same perspective. Anyways, there's a lot of different discussions, extensions that one can have. And that's all for the introduction. Thank you very much.